Hey everybody, welcome to AlgoExpert. In this video, we're going to be covering the bubble sort algorithm. This is a pretty simple sorting algorithm. It's very intuitive, easy to wrap your head around, fairly straightforward to implement in code. But that being said, it's an important algorithm to understand because it really teaches you a lot about complexity analyses and it prepares you for tougher, more optimal sorting algorithms like merge sort, quick sort, and heap sort. So in this video, we're going to dive into bubble sort and we're going to explain exactly how the algorithm works. So the goal is to sort a list of numbers, okay? We've got this list of numbers in front of us and we want to sort it in ascending order. In other words, we want the smaller numbers to come before the larger numbers. So how does bubble sort work? Well, basically, we're going to iterate through this array multiple times. And each time we iterate through it, we're going to perform swaps to place numbers in their correct order. So more precisely, the first time we iterate through this array, we're going to traverse through it from the start all the way to the end. And at any point, at each number that we're at, we're going to check if the current number and the number that comes right next to the current number. So in the first example, we start at 8, 8 being our current number and 5 being the number that comes after 8. And we check if these two numbers are in the correct order. In other words, is the current number smaller than or equal to the next number? Are they sorted? If they are, then we just move on, we just disregard them and we move on to the next number and we continue traversing the array, checking if numbers are in the correct order. But if they're not in the correct order, like in this case, it's pretty obvious that 8 and 5 are not in the correct order. 8 should come after 5. Then we swap the numbers. Okay, we swap the numbers in place, and then we continue traversing the array. We continue moving on to the next number and continue doing the same thing. And then once we've finished traversing the array once, so we get to the end, right? We ask ourselves, did we perform any swaps? Were any two numbers out of order in this particular iteration of the array? If yes, that means that the array was not sorted, so we have to redo our entire iteration once more just to check if it's sorted now. If we didn't do any swaps, then the array was sorted and we're done. We're done with the algorithm. We can just return the array. And it's important to note here that bubble sort occurs in place, meaning whenever we swap two numbers in the array, we're doing it in place. We're not putting them in some kind of other helper array, and that differentiates bubble sort from some other sorting algorithms that do use other arrays that aren't in place. But so let's actually go through this flow, this logic flow, on our example here. We start with the number 8. We start at the first iteration through the array at the first number 8, and we compare it to the next number 5. So is 8 less than or equal to 5? Are they in the correct order? The answer is no, they're not. So we have to swap them. So we're going to erase 8 and we're going to erase 5, and we're going to swap them like so. Okay, now we move on to the second point, which is now 8, and we compare 8 and 2. Is 8 less than or equal to 2? Are they in the correct order? No, they're not, so we swap them. So we're going to erase them, we're going to put 2 here and 8 here. Now we compare 8 to 9. Is 8 less than or equal to 9? Yes. So 8 and 9 are in the correct order. So we leave them as they are, and we move on to 9. Now our current number is 9. Compare 9 to 5. They're not in the correct order, so we swap them, erase them, put the 5 here and the 9. Now we compare 9 to 6. Again, they're not in the correct order, so we swap them. 6 and 9. And lastly, we compare 9 to 3. They're not in the correct order, so we swap them. 3 and 9. Now, one thing that's important to note here is that what we've effectively done in this first iteration is we've said the last number here is in the final correct order. Because at each point, right, we're comparing the orders of numbers. So naturally, whenever we get to the largest number in our array, which in this case was 9, we know it's going to end up being swapped all the way to the right. And if it doesn't get swapped all the way to the right, that means that the rightmost number is itself the biggest number. Like imagine we had, a 10 here at the very far right of the array, then that 9 wouldn't have been swapped with the 10, and the 10 would be our largest number. But so in this case, 9 is our largest number, and so we never need to actually check this 9 again. So we can do a very small optimization that's not actually going to affect our time complexity analysis, but it's still an optimization nonetheless. We no longer have to iterate through the entire array for the second loop. We can just iterate through the first numbers, stopping at 9. So in fact, what I'm going to do is I'm going to write 9 instead of writing it in white. I'll write it in purple to show that this is the final position of the 9. Now we ask ourselves, did we do any swaps this iteration? Yeah, we did a bunch of them. So we have to restart at the beginning and loop through the entire array again and perform all of our checks. So we start at 5. Is 5 less than or equal to 2? No, it's not. So we swap 5 and 2. So 2 is going to come here, and 5 is going to come here. Is 5 less than or equal to 8? Yes, it is. So we don't touch these two numbers. Now we move on to 8. Compare 8 and 5. Is 8 less than or equal to 5? No, it's not. So we swap them. We've got 5 and 8. Now we compare 8 to 6. They're not in the correct order, so we swap them. 6 and 8. Now we compare 8 to 3. They're not in the correct order, so we swap them. Put 3 here and 8 here. And now we're done. We're at the end of our array, because, again, we're not going all the way to this 9, because the 9 is in the final position. So we're in the final position of our 8. We're done with the 8, so we can actually erase it and write it in purple. So now we've locked down two numbers, 8 and 9. But we did perform swaps this time around in this traversal of the array. So we go back all the way to the beginning, and we reiterate through the array. We start at 2, compare 2 to the next number, which is 5. Is 2 less than or equal to 5? Yes, it is. They're in the correct order. We don't touch them. Then we go to this 5. Is 5 less than or equal to 5? Yes, it is. It's equal to 5. So 5 and 5 should be next to each other. They're in the correct order. We move on. We don't touch them, and we move on to this 5. Are 5 and 6 in the correct order? Yes, there are. Don't touch them. Then compare 6 to 3. These two numbers are not in the correct order, so we swap them. Put 3 and 6. Okay, so now we have 6 here, and wait, we just reached our 8, which was in the correct final position, so we're done with this loop. We can stop here, and we can actually erase this 6 and put it in purple because it's the final position of the 6. Because we did perform a swap between the 3 and the 6, we have to reiterate through our array and check that it's in sorted order. So we start at the 2 and 5 correct order, so we don't do anything. 5 and 5 correct order, don't do anything. 5 and 3, not the correct order, so we swap them. Put 3 here, and now we've reached the end, so we can put 5 in purple. We did perform a swap, so we're not done. We have to reiterate through the array, through the first 3 numbers this time around. So we start at 2 and 5 are in the correct order, don't do anything. Move on to 5 and 3 are not in the correct order, so swap them. Erase the 3, put the 3 here. 5 is in the last position, so we can put it in purple. And now, because we did perform a swap, we redo this entire logic. start of the 2. 2 and 3 are in the correct order, so we move on to 3, and wait, we're done. We're at the final thing that we needed to check in this loop. So now, because we didn't perform any swaps in this final loop, we are actually finally done. And I can erase the 2 and the 3 and put them in purple just to show that they're in their final position. And if we really check just from a sort of intuitive point of view, is this array actually sorted? Yes, it is. 2, 3, 5, 5, 6, 8, 9. So that's how bubble sort works. That is bubble sort in action, really. And before we dive into the code walkthrough, let's look at the space-time complexity analysis of this algorithm. In terms of space, bubble sort is actually going to run in constant time. So space is going to be O of 1 because the algorithm runs in place, right? All our swaps were done in our input array. We were given an input array, and all of our swaps were performed on that input array. We didn't allocate additional memory to implement a bubble sort. So the space complexity is going to be O of 1. Now, the time complexity is going to be O of n squared, where n is the length of our input array. Why is it O of n squared? Well, it's O of n squared because we are looping through the array multiple times, right? We're looping through the array until the array gets sorted. And in the worst case, or even in the average case, we're going to be doing a bunch of for loops through this array. And so its time complexity is going to be O of n squared. Now, it is important to know that for bubble sort, the best case scenario is actually not O of n squared, it's actually O of n, and that occurs when you're given a sorted array. If we were applying bubble sort on this array, the final array that we got at the end, which is sorted, well, what would we do? We'd traverse it once. We'd start at 2, compare it to 3. They're in the correct order. 3 and 5, correct order. 5 and 5, 5 and 6, 6 and 8, 8 and 9. So we'd iterate once through there. Then we'd ask ourselves, did we perform any swaps? No, we didn't. So we're done. We're in sorted order. And that was just O of n time, right? But that only happens if we get an array that is in sorted order. Okay? Whereas if we're given arrays that are not in sorted order, on average, and in the worst case, our algorithm is going to run in O of n squared time because we're doing so many for loops through the array. All right, so now let's dive into the code walkthrough to see what this algorithm looks like when written in code. All right, so we've got our bubble sort function defined, and it takes in an array of integers. Now, the way I like to implement bubble sort is to keep track of whether or not the array is sorted in an isSorted variable. So we're going to declare an isSorted variable to false at the beginning. At the beginning, we assume that the array is not sorted. And then we say while not is sorted, in other words, while the array is not sorted, we're going to do stuff. We're going to do that traversal with all the checks that we went over in the code or in the conceptual overview part of this video. So while not is sorted, we tentatively set the isSorted variable to true. We tentatively say, okay, we're gonna think that maybe the array is sorted this time around. And then we jump into our for loop. For I in range len of array -1. The reason we only go to the before last number in the array is because, remember, at every point, we're checking the current number to the next one, compared to the next one. So we don't need to go all the way up to the final value in the array. We only need to go up to the before last value in the array. So this range here is going to take len of array -1, where this is excluded in the range, right? So for I in this range, we check if the current number, if array of I, is greater than array of I plus 1. And if it is, then the two numbers at array I and array I plus 1 are out of order. So we swap them, and we can have a function, a helper function, that is going to swap. It's going to take the index I, the index I plus 1, and our array, and it's going to swap those two values. And so here, the important point now is to say, if we get into this if statement, if we ever find ourselves in this if statement, then we want to set our isSorted variable to false, because we want to say our array was clearly not sorted. And then finally, we return at the end our sorted array. And if we want to implement our helper function, our swap function, we can implement it here. It takes in two indices plus our array, and we can just say array I, array j is going to be equal to array j, array I. Now, depending on your language, this helper function might be a tiny bit more involved. It might take more than just one line to implement, but regardless, the point is you want to implement your swap function here so you can use it inside your if statement. Now, recall that during the conceptual overview, I mentioned that we can implement a very slight optimization by not checking through our entire array in each of our for loops, because at each loop, the final number is going to be in its final position. Like in our example, the at the beginning, the 9 after the first loop was in its final position because it was the greatest number. And then in the second loop, both the 8 and the 9 were in their final positions. Then in the third loop, the 6, 8, and 9 were in their final positions, etc. So what we can do here is we can say, right above the while loop, we can declare a counter variable that we set to 0. And the for loop can go, instead of going all the way to len of array minus 1, it can go to len of array minus 1 minus counter. And then finally, in the for loop here, we want to, or in the while loop, sorry, we want to increment our counter by 1 every time. So every time that we finish a for loop and that we, tentatively go back into the while loop, we increment our counter, which is going to say that in the next for loop, we're going to only go to one position before the position that we went to in this current loop. And that's a very small optimization. It doesn't really affect the time complexity analysis, but just in practice, it makes your algorithm, better. And so that is bubble sort for you. Very, very simple and straightforward, but nonetheless very important. It runs in O of n squared time in the worst and average case, and O of 1 space. And lastly, I will mention that this swap function here, you don't necessarily need to have it be a helper function. You could have put this, line 15 here directly if you wanted to. Depending on your language, the logic behind the swap function, like I said, might be more involved. So if I were you, I would abstract that out of the bubble sort function, but it's up to you. It's something to discuss with your interviewer. Anyway, I hope this video was helpful. I hope it was informative, and I'll see you in the next one.